Ever wondered what really happens after you take that first bite? I mean, it's more than just food disappearing, isn't it?
Oh, absolutely. It's this incredibly complex, fascinating, and sometimes pretty surprising internal journey your body takes, every single time you eat.
So today, we're doing a deep dive into one of your most fundamental systems, the human digestive system.
Yep.
We've pulled together some really detailed sources that lay out the whole process, basically from mouth to, well, the final exit.
Our mission today really is to unpack this intricate system. We want to highlight its incredible efficiency, who the key players are, and even some historical bits that show just how long we've been trying to figure this all out.
Yeah.
By the end, you'll have, I think, a whole new appreciation for what your body's doing, like silently all the time.
Okay, let's dive in then. What's really kind of amazing is that digestion actually kicks off before any food even hits your tongue. It's this thing called the cephalic phase.
That's exactly right. Just, seeing food, smelling it, even just thinking about your favorite pizza
Yep.
can trigger your brain. It sends signals, gets your gastric glands ready, prepares for action. Then, okay, food enters the mouth and the real action starts, both mechanical, chewing, and chemical breakdown.
Right.
Your mouth has these salivary glands, several pairs, plus lots of tiny ones constantly making saliva. And saliva seems simple, but it's actually this really complex mix.
So it's not just wet stuff.
Not at all. It moistens food, softens it up, makes it
Oh.
easier to swallow. It even protects your teeth with mucus, specifically a protein called mucin.
Okay, so saliva's doing a lot more work than I thought.
Definitely. And here's where it gets really interesting, I think. Saliva has key digestive enzymes.
Like what?
Well, amylase, for one, it jumps right in, starts breaking down starches into simpler sugars, maltose, dextrose,
Right away.
instantly. And then there's lingual lipase. It begins breaking down fats. This is super important for babies, actually, because their main fat enzyme system isn't fully online yet.
Oh.
And beyond just digestion, saliva has antibodies, so it plays an immune role. Plus, it's got this unique protein, haptocorin, that acts like a little bodyguard for vitamin B12.
The bodyguard.
Yeah, it grabs onto B12 and shields it through the really harsh, acidic stomach environment. Pretty clever.
Incredible. And the tongue, I mean, it seems like just a muscle, but it's obviously doing a lot here too.
Oh, massively.
Yeah.
Your tongue is this fleshy, muscular sensory organ. It's where you first get that sensory input from food via your taste buds.
Right, the taste buds.
If the taste is good, the tongue just springs into action, moves the food around, mixes it with more saliva. It's got two sets of muscles, which gives it amazing mobility for chewing and getting that food ready to swallow.
So why do we have these specific tastes, like the 5 basic ones?
Right, good question. Taste itself is chemoreception, right? It happens in these specialized receptors, mostly on the tongue, but also surprisingly a bit on the epiglottis and even the upper esophagus.
Ah,
So the 5 basic tastes: saltiness, sourness, bitterness, sweetness, and umami. Think of them as signals from evolution. Signals.
yeah. Saltiness and sourness help you manage salt and acid balance. Bitterness, well, that's often a warning sign for poisons. Lots of plant defenses are bitter.
Okay, that makes sense.
Sweetness signals energy carbs, basically, especially once that salivary amylase starts working. And umami points towards protein-rich foods.
So your brain's making super quick decisions.
Instantly.
Mm-hmm.
Is this safe? Is it nutritious?
Yeah.
And taste works so closely with smell, doesn't it? To create those complex flavors we enjoy.
Right. And then the teeth, can't forget those, the grinders.
Exactly. Your teeth made of dentin, covered in super hard enamel, the hardest stuff in your body.
Harder than bone.
Yep. And they're specialized. Incisors cut, canines tear, and the premolars and molars, they do the heavy-duty chewing and grinding.
And all that chewing is important because
It massively increases the surface area of the food, makes it much easier for those digestive enzymes we talked about to get in there and do their job.
So all this chewing, mixing with saliva and mucus, it forms this soft, wet ball of food called a bolus, ready for the next step.
So bolus formed, ready to swallow. There's like
Yeah.
a traffic controller at the junction, right? The epiglottis.
That's a great way to put it. The epiglottis, it's this neat little flap of elastic cartilage right at the entrance to your larynx, your voice box. It even has some taste buds.
Really?
Yeah. But its critical job, its life-saving function, is folding down when you swallow. It acts like a lid, sealing off your windpipe, the trachea.
So food doesn't go down the wrong way.
Exactly. It directs the food safely towards the esophagus. And if by chance something does slip into the larynx, your body has this powerful cough reflex. It's like a built-in eject button to protect your lungs. Amazing system.
Okay, so from the mouth, the bolus moves into the pharynx.
Right, the pharynx, it's a shared space. Air goes through it, food goes through it.
How does that work?
Well, when you swallow, the body prioritizes the food. It momentarily blocks the airway. Then muscles in the pharynx kind of push the food along into the esophagus.
And the esophagus, that's the food pipe, basically.
Precisely. It's a muscular tube, maybe 25 centimeters long, give or take. Connects the pharynx down to the stomach.
Is it just a smooth tube?
It's muscular, and it has sphincters, like muscular gates at both ends. The upper one opens to let the bolus in when you swallow.
And the lower one?
The lower esophageal sphincter, yeah. That one's super important. It guards the entrance to the stomach and normally stays tightly shut.
Why is that so crucial?
To keep all that strong stomach acid and digesting food in the stomach, preventing it from splashing back up into the esophagus.
Ah, heartburn.
Exactly. When that sphincter doesn't work quite right or it relaxes when it shouldn't, you get reflux. That's the burn.
Okay, so how does the food actually get down the esophagus? Does it just drop?
You'd think so, but no, not just gravity. It's moved along by this rhythmic, wave-like muscle contraction. It's called peristalsis.
Peristalsis.
Yeah, these waves squeeze the bolus downwards, and this peristalsis, this muscular wave action, it doesn't stop at the esophagus. It continues all the way through your digestive tract.
Really, all the way?
Yep, it keeps everything moving along. In the stomach, this motion helps mix everything up and starts forming this semi-liquid stuff called chyme.
Chyme, got it.
And actually, speaking of things nearby, the diaphragm, the big muscle under your lungs that helps you breathe,
Yeah?
it plays a small but interesting role in digestion, too. It helps anchor your liver in place, and there's even a little muscle attached to it that helps widen a bend in your small intestine, easing the passage of food.
Huh. Who knew? Okay, so the bolus, pushed by peristalsis, gets past that lower sphincter and arrives in the stomach, the command center, right?
You could definitely call it that. And it's way more than just a storage bag. It's a real chemical processing plant.
It looks kind of J-shaped in diagrams.
Typically, yeah. And it's incredibly stretchy. An adult stomach can comfortably hold about a liter of food and liquid. A newborn's. Only about 30 milliliters. And inside, that peristalsis churning continues, mixing the food vigorously with really potent digestive juices.
Gastric juice. What's in that?
Primarily, it's hydrochloric acid, really strong acid, and some sodium chloride. There's a hormone called gastrin that tells the stomach to produce this juice.
And the acid does what?
It does a few things. It kills a lot of bacteria, and importantly, it activates digestive enzymes. The main protein-digesting enzyme is pepsin.
Pepsin.
Yeah, but here's the clever bit. The stomach doesn't secrete active pepsin. It secretes an inactive form called pepsinogen.
Like a safety lock.
Exactly. So it doesn't start digesting the stomach wall itself. Only when pepsinogen hits the strong acid does it activate and become pepsin, ready to chop up proteins.
Smart. Any other enzymes?
There's also gastric lipase, which starts working on fats, but honestly, it's not as powerful as the fat enzymes that come into play later on.
So with all this acid and protein chopping enzyme, how does the stomach not just digest itself?
Excellent question. Protection is key. The stomach lining is coated in this thick, slimy layer of mucus. Millions of tiny glands are constantly producing it. It forms a physical barrier against the acid and the pepsin.
Okay, that makes sense. But earlier you mentioned vitamin B12 needed protection through the stomach acid. How does that survive?
Ah, yes. The B12 journey. It's a fantastic example of teamwork. It's a two-step process. Remember that haptocorin protein from saliva?
The bodyguard, yeah.
Right. It binds to B12 in the mouth or throat and protects it all the way through the stomach's acid bath. Then, when the chyme moves into the less acidic small intestine, stomach enzymes break down the haptocorin.
Freeing up the B12.
Exactly. And just at that moment, another protein called intrinsic factor, which is made by specific cells in the stomach lining.
Okay.
Intrinsic factor steps in, binds to the now free B12, and carries it further down the small intestine to where it can finally be absorbed. It's like a carefully planned handoff.
Wow. Quite the relay race. So what leaves the stomach then?
What leaves is this thick, semi-liquid mixture called chyme. Making it can take, I don't know, an hour or two, maybe longer, depending on the meal.
Okay.
This time then passes, bit by bit, through another muscular gate, the pyloric sphincter, into the very first part of the small intestine, the duodenum.
Right, the duodenum. And once that chyme gets there, it's not working alone, is it? This is where those accessory organs really jump in.
Absolutely. This is where the orchestra really comes together. You've got the pancreas, the liver, the gallbladder, all working in perfect sync with the small intestine.
Let's talk pancreas first. I know it does insulin stuff, blood sugar.
Right, that's its endocrine role. But for digestion, it's a powerhouse exocrine gland. It produces pancreatic juice.
Okay, and what's special about that?
Two main things. First, it's alkaline. It contains lots of bicarbonate ions. These are crucial for neutralizing that superacidic chyme coming from the stomach. The intestine needs a more neutral environment for its enzymes to work.
Ah, okay. Neutralizing the acid. And the second thing,
Enzymes, a whole cocktail of them. It makes powerful enzymes to break down proteins, fats, and carbohydrates. Think trypsin and chymotrypsin for proteins, lipase for fats, amylase for carbs.
the full toolkit.
Pretty much. And again, just like pepsin in the stomach, many of these are released in inactive form zymogens, so the pancreas doesn't digest itself. They only switch on once they safely reach the intestine.
It's a very clever system.
Yeah.
Okay, what about the liver? Huge organ, does tons of things.
Yeah.
What's its main digestive job?
You're right. The liver's a multitasker: detox, protein building, glucose storage. But for digestion, its primary role is making bile acids and lecithin. These are essential for breaking down fats. And it produces the bile fluid itself.
Bile.
Bile is mostly water, but it contains those bile salts, mucus, pigments like bilirubin, which comes from breaking down old red blood cells, gives waste its color,
Yeah.
and fats. This bile gets sent to the gallbladder.
Right, the gallbladder. It doesn't make bile, it just stores it.
Exactly. It's a little storage sac tucked under the liver. It holds the bile produced by the liver, and importantly, it concentrates it, makes it more potent.
So how does it know when to release the bile? It can't just be leaking out all the time?
No, it's very precise. It's triggered by a hormone called cholecystokinin, CCK.
CCK.
Yeah. As soon as fatty chyme enters the duodenum from the stomach, it triggers cells there to release CCK into the bloodstream. CCK travels to the gallbladder and signals it to contract.
Go squeeze out the bile.
Right into the duodenum, just where it's needed to tackle those fats.
And what does the bile actually do to the fats?
Its key role is acting as an emulsifier, like dish soap breaking up grease. Bile salts surround large fat globules and break them into much, much smaller droplets called micelles.
Micelles, okay.
This massively increases the surface area of the fat, so the fat-digesting enzymes, the lipases mainly from the pancreas, can attack them much more effectively. Bile also helps you absorb fat-soluble vitamins like vitamin K.
So without bile, fat digestion would be really difficult.
Extremely inefficient, yes. And if things go wrong with the bile, maybe too much cholesterol or the gallbladder doesn't empty properly, those components can crystallize and form gallstones.
Ouch. Okay, so we've got neutralized chyme, pancreatic enzymes, and bile all meeting in the duodenum. Now we're properly in the small intestine, the main event for digestion and absorption, right?
Absolutely. This is where the vast majority of digestion and nutrient absorption happens.
You mentioned neutralization is key.
Crucial. That bicarbonate from the pancreas, plus some bicarbonate-rich mucus from glands in the duodenum itself, and the alkaline bile, they all work to bring the pH up, protecting the intestine and letting all the enzymes do their best work.
And the main job now is breaking stuff down small enough to absorb.
Exactly. Breaking down carbohydrates into simple sugars, proteins into amino acids, fats into fatty acids and glycerol. Small molecules that can pass through the intestinal wall into your body.
And how does the small intestine actually absorb all this stuff? It must have a huge capacity.
It does, thanks to its incredible structure. The lining isn't smooth. It's covered in these specialized cells called enterocytes, and the lining is folded. And on those folds are millions of tiny finger-like projections called villi.
The villi. I heard of those.
And then each cell on the surface of the villi has even tinier projections called microvilli. All these folds, villi and microvilli, create this absolutely enormous surface area.
Like how enormous?
Some estimates say if you flattened it all out, it could cover a tennis court.
No way. Inside your belly.
It's incredible. This huge surface area is vital for efficiently absorbing all those digested nutrients. Some final digestion even happens right on the surface of the microvilli by enzymes located there.
Okay, tennis court surface area.
Yeah.
Wow. What about those fats, the micelles? How do they get absorbed? It's different, right?
It is slightly different. Once fats are broken down, they get repackaged inside the intestinal cells into these little particles called chylomicrons. Think of them as tiny fat delivery trucks.
Okay.
Now, unlike most other nutrients that go directly into the bloodstream capillaries in the villi,
Yeah.
these chylomicrons, these fat trucks, are too big for that. They get absorbed into tiny lymph capillaries called lacteals, which are also present in the villi.
Lacteals. So they go into the lymph system first.
Exactly. This mixture of lymph and chylomicrons creates a milky-looking fluid called chyle. This chyle travels through the lymphatic system and eventually gets dumped into your bloodstream near your heart. So fats take a slightly different route.
Fascinating. And the small intestine isn't just one long tube, is it? It has sections.
Right. Three main sections. First is the duodenum, the short C-shaped part right after the stomach. That's the main mixing bowl, receiving chyme, bile, pancreatic juice.
Okay.
Then comes the jejunum, the middle section. It has lots of prominent circular folds to maximize that surface area. This is where most of the absorption of sugars, amino acids, and fatty acids happens.
Jejunum. Got it.
And finally, the ileum. That's the last and longest part. Its main jobs are to absorb vitamin B12, remember, bound to intrinsic factor, and also to absorb bile acids so they can be recycled back to the liver and mop up any remaining nutrients that escaped absorption earlier.
Okay. So from the ileum, what's left moves on. Where does it go next?
It moves into the final stages. First, it passes through the ileocecal valve, another one-way gate into the cecum.
The cecum.
Yeah, it's this pouch that kind of marks the beginning of the large intestine. That ileocecal valve is important. It slows down the passage from the ileum, giving a bit more time for absorption. And fun fact, the appendix is attached to the cecum.
Ah, the appendix. Okay. So after the cecum, we're into the large intestine proper.
Correct. The large intestine, which includes the colon, the rectum, and finally the anus.
And things move much slower here. Right?
Much, much slower. Transit time through the large intestine can be anywhere from, say, 30 to 40 hours, sometimes longer.
Wow. Why so slow? What's its main job?
Its main functions are really about reabsorbing water from the remaining indigestible food matter. It also absorbs some electrolytes, some minerals, and critically, it's home to trillions of gut bacteria, the gut flora or microbiome.
The microbiome. We hear a lot about that.
Yeah, and these bacteria do important work. They ferment some of the indigestible material, like certain fibers, producing vitamins like some B vitamins and vitamin K and short-chain fatty acids that can actually nourish the colon cells.
So it's mostly about water absorption and bacterial action.
Largely, yes. What's left after the water's removed and the bacteria have done their thing is the semi-solid waste we call feces.
And how does that get moved along and eventually out? Still peristalsis.
Yep, coordinated peristalsis is still the driver. The large intestine has specialized muscle layers. There's an outer layer of longitudinal muscles that are gathered into three bands called the taenia coli.
Taenia coli.
Yeah, these bands are slightly shorter than the colon itself, which causes the colon wall to bulge outwards between them, creating those characteristic sacs or pouches called haustra.
Ah, those bulges you see in diagrams.
Exactly. And then there's an inner layer of circular muscle. These muscle layers work together to slowly propel the feces along, segment by segment, towards the rectum, ready for elimination.
Incredible. Yeah. Beyond the main organs, though, you mentioned support systems. How does this whole massive operation get its blood supply? It must need a lot of energy.
It definitely does, especially after a meal. The digestive system has a really rich blood supply from major arteries branching off the aorta.
Like which ones?
Well, there's the celiac artery supplying the upper part stomach, liver, spleen, pancreas. Then the superior mesenteric artery takes care of most of the small intestine and the first part of the large intestine.
Okay.
And the inferior mesenteric artery supplies the rest of the large intestine down to the rectum.
And the blood flow changes.
Oh yeah, dynamically. Blood flow to the gut can increase significantly, peaking maybe 20 to 40 minutes after you eat, and it can stay elevated for a couple of hours while digestion and absorption are in full swing. It's diverting resources to where they're needed.
Makes sense. And maybe the most fascinating support system, the second brain, the enteric nervous system.
Ah, yes, the ENS. It truly is like a second brain. We're talking about something like 100 million neurons. That's more than in your spinal cord.
100 million. Where are they?
They're embedded right there in the walls of your entire GI tract, from the esophagus all the way down to the anus. They're organized into these intricate networks or plexuses.
So the gut can think for itself, kinda.
To a large extent, yes. It can control gut motility, secretion, blood flow, largely independently of the actual brain. That's why it gets called the second brain.
But the main brain still has some input.
Oh, definitely. It's influenced by the autonomic nervous system. The parasympathetic system, mainly via the vagus nerve, generally stimulates digestion, the rest, and digest functions.
Okay.
And the sympathetic system, the fight or flight response, tends to slow digestion down, diverting resources elsewhere during stress. It's this complex interplay, constant communication.
It's just staggering how complex this all is.
Yeah.
Thinking about how it develops, it must be incredible to watch unfold in an embryo.
It truly is. The very early gut tube actually forms from parts of the yolk sac. And then around the 4th week of pregnancy, some really key movements happen. The stomach rotates, settling into its position on the left side.
It rotates.
Yep. And at the same time, little buds start to grow out from the duodenum. These will eventually develop into the liver, the gallbladder, and the bile ducts. It's a precisely choreographed sequence, biological engineering at its finest.
It sounds so robust, but obviously things can go wrong.
Okay.
We touched on heartburn and gallstones.
Yeah.
What are some other common issues, maybe further down the line?
Yeah, despite its resilience, every part is vulnerable. You can get infections, bacterial, viral, fungal, think gingivitis or thrush in the mouth. Medications can cause side effects too.
Right.
In the esophagus, besides reflux, you might have things like Schatzki rings, which are these narrowings that make swallowing difficult. The stomach can have issues like gastroparesis, where it empties too slowly, or gastritis, which is inflammation, or those peptic ulcers, often linked to the H. pylori bacteria.
Okay. And in the intestines?
Malabsorption is a big category. This means you're not absorbing nutrients properly. It could be due to infections or missing certain enzymes, or conditions like celiac disease. That's an autoimmune reaction to gluten damaging the small intestine lining.
Celiac disease, right.
Then in the large intestine, you have things like diverticulitis, where those pouches, the haustra, get inflamed or infected, and inflammatory bowel diseases like Crohn's disease,
Crohn's.
which can affect anywhere from mouth to anus, and ulcerative colitis, which mainly affects the colon and rectum. Both of those, unfortunately, increase the risk of developing colorectal cancer later on.
That's serious.
It is. And then there's irritable bowel syndrome, IBS, super common, causes cramping, bloating, changes in bowel habits. It's a functional disorder, meaning the gut looks normal but doesn't work right. Plus, things like parasitic infections like giardiasis. Lots can potentially go wrong.
How do doctors even figure out what's happening in there?
Various ways. Imaging is key. Sometimes they use things like a barium sulfate series. You drink this chalky liquid and it shows up on x-rays, outlining the shape and movement of your GI tract. Endoscopies, colonoscopies, lots of tools.
And cancer.
Yeah.
You mentioned the risk with IBD. How big a problem is digestive system cancer overall?
It's a major health issue, unfortunately. The stats are sobering. For 2023 in the U.S., estimates were around 348,000 new cases of digestive system cancers and about 172,000 deaths.
Wow. Which types are the biggest killers?
The leading causes of death in that category are colorectal cancer, then pancreatic cancer, which is notoriously difficult, followed by liver cancer, esophageal cancer, and stomach cancer.
That's significant.
It really is. And it's interesting, even things like bile acids, which are essential for digestion, if they reach abnormally high levels, they've been implicated as potential carcinogens in the gut. It's all about balance.
Even pregnancy can affect digestion, right? Like gestational diabetes?
Yes, that's considered a potential digestive disorder during pregnancy. It affects how your body processes sugar and can sometimes lead to other complications as well. The hormonal shifts during pregnancy can impact the digestive system in various ways.
Okay, so we've covered how it works, development, problems. How did we even figure all this out? What's the history of understanding digestion? Must have been a mystery for ages.
Oh, for centuries. Our understanding has definitely evolved. If you go way back to the 11th century, someone like Avicenna, a great Persian physician, he believed digestive problems caused gas pretty accurate and suggested lifestyle changes.
Ahead of his time.
In some ways. But for a long time, the stomach was seen quite negatively. It wasn't until the mid-17th century that Jan Baptist van Helmont gave the first chemical explanation of digestion. That was a big shift.
And the acid discovery.
That was William Prout in 1823. Discovering hydrochloric acid in gastric juice was huge. It started to explain the chemical power of the stomach.
And then there's that amazing story about William Beaumont, the army surgeon.
Ah, yes. 1825. He had a patient with a gunshot wound to the stomach that never fully closed, creating a sort of window. Beaumont literally watched digestion happening live.
Incredible.
He described the churning motion, tested how different foods digested, earned him the nickname Father of Gastric Physiology. His direct observations were revolutionary.
So observation, then chemistry.
Yeah.
What came next?
Well, Pavlov, famous for his dog salivating.
Right.
In 1895, he showed that stomach acid secretion was linked to the nervous system, specifically the vagus nerve, a brain-gut connection.
Okay.
Then the 20th century brought a focus on hormones and enzymes. Discoveries like secretin and gastrin showed this complex chemical signaling controlling everything. Later came the drugs H2 blockers in the 70s, proton pump inhibitors in the 80s that could actually control stomach acid production, game changers for ulcers and reflux.
And the ulcer bacteria.
That was Marshall and Warren in 1983. Linking Helicobacter pylori to ulcers was Nobel Prize-winning work. It completely changed how we treated stomach ulcers from stress management and bland diets to antibiotics.
Wow. What a journey of discovery. Any other surprising historical bits?
Well, here's a fun one related to ancient habits. Art historians noticed that in depictions of ancient Roman banquets, the diners are often reclining on their left sides.
On their left. Why?
The theory is it actually aids digestion. Lying on your left side uses gravity and the natural curve of the stomach to help food settle and process more comfortably. It gives the stomach more room to expand downwards.
Huh. So those Romans knew a thing or two, maybe without even knowing the science.
Seems like it. Practical anatomy, perhaps.
We have really journeyed deep into this incredible inner world today, haven't we? The human digestive system. From just thinking about food right down to the very end, it's just a testament to the body's efficiency and complexity.
It really is. It's this beautifully coordinated dance, isn't it? Every part playing its role, transforming food into energy and building blocks while also protecting us. It's an amazing internal symphony, constantly working away.
So what stands out most to you listening in about this incredible system? Maybe next time you sit down for a meal, you'll have a whole new appreciation for that silent, intricate process happening inside. And hey, maybe you'll even think about which side to recline on afterwards.